Okay. Let's learn about waves in 2 dimensions. So a lot of the same ideas that applied for like waves in 1 dimension, which would be like, waves in a string and so on, also apply to waves in 2 dimensions. So we're still going to have things like crests, troughs. We're still going to have like amplitude, right? Velocity of the wave. It's still going to have a direction of travel, okay? But now the energy is not restricted to traveling in a medium that is like only 1 dimension, like a string. So now we're going to talk about, let's say that we have, and water is a really good example of this. We have a surface through which a wave can travel with sort of 2 degrees of freedom, right? So, in this case, you could think of it as only having like an x-axis that the wave can move in. So it can either move one way or the other. Now we have like a y-axis as well as an x-axis. Okay, so we'll use a little bit of math terminology. Now, if our source, this is the application of the energy, and we can imagine that we're looking down on top of a pool or some, trough filled with water, and we have our source here, what we will see is that waves will emanate outward. I'm going to try to use nice round circles here, if I can. See what happens. Okay. Don't worry, I'll arrange them in a nice shape here in a minute. I think I will. There. Okay. So if the disturbance is at the middle, it's almost good. There. Okay. These waves travel out. Now what we're imagining here is that maybe these lines represent, say, a crest. Okay. And the blank spots behind represent a trough. So this is a method of representing waves emanating out from a source in 2 dimensions. So we have some new names we have to talk about now. Oh, for goodness sake. We have some new names we have to talk about now. And we call these things wave fronts. Wave fronts. Okay? So each line represents a wave front. Now you can consider that to be, either a crest or a trough. But if you had, say, like some sort of detector or whatever sitting here, as these wave fronts ran into it, you'd get your frequency out of there. So each wave front represents a distance between itself and the next wave, or if you want, a wavelength. So the distance between 2 fronts is the wavelength. Okay, so wavelength we've seen before. How aggressively we're agitating the water will, increase or decrease the amplitude of the wave. You don't really show that on this type of a picture, but something else that you do show is what's called a wave ray. So wave rays are arrows that are showing the direction of travel of the wave, and basically, I want an arrow. I want a blue arrow. Why is that on an arrow? There we go. For goodness sake, I'm learning. Guys, I'm still learning. There we go. Okay, so in this case, our wave rays are going to emanate out kind of in all directions here. All right? Something to realize about wave rays is that they are always perpendicular to a wave front. All right? So a wave ray is perpendicular to a wave front at all points. So wave rays show, I guess if you want, velocity of the wave. Specifically, the direction part of the velocity vector. Okay, you'd likely have to talk about the magnitude of that velocity separately, but these are showing the direction of travel of the wave. So in this case, what this is implying is that waves travel outward from the source in all directions. Okay, so wave rays are vector arrows they are placed at 90 degrees to wavefronts. So these are your circular waves in 2D up here. So that is waves emanating from a single source, but we can also cause what are called plane waves in the same scenario, okay? So we have a pool of water, and instead of having a single point source, we now have a linear source. So like imagine that you lay a straight ruler in here and you start to oscillate that ruler either back and forth or up and down. Both will cause the waves to happen. Okay, what you'll get is you'll get a series of waves moving along like this. Okay, now these should all be linear, but I'm freehand drawing, so if we include the wave rays here, okay, they're going to be like that. So we'll just relabel everything in terms of the plane waves. So these are fronts. Okay. This distance is your wavelength. Okay. And these are your wave rays, showing the direction of travel of the wave. Okay. This is your linear source. Linear because it's in a line. So these are often just called plane waves, planar waves. Like linear waves or plane waves. Okay, so linear or plane waves. So fronts here, rays here. Remember, rays are always arrows, okay, because they got to show the direction of travel of the wave. So the next thing we're going to look at is we're going to talk about reflection. Okay, so to do an example of reflection, we have to imagine that in that pool that we had before, oops, I don't want that. Oh my goodness gracious. There we go. Okay, so we're going to imagine that this is our pool again. Okay, we're going to put a little barrier in the pool, or a wall, or a bulkhead, or call whatever you want. Okay, so this is meant to represent like a little wall. Okay, and then we're going to have a linear source of waves up over here. Okay, so right here, so this is our source, it's vibrating back and forth. But all we're going to draw here is the incident wave ray. Okay. So there's my wave ray. So what we're implying here is that we have linear waves moving along. I'll draw a few more, right? So there's a few waves coming through. And we're just going to leave it at that, but we're going to realize that there's waves all the way along here. Okay? So these waves are striking this surface at some angle. Now to measure this angle, we're going to draw what's called a normal. All right? So a normal is just a line that is drawn perpendicular to a surface. So there's our normal. I'm just going to change the color of the normal so it stands out a bit more. There we go. Okay. We're going to say this line is called a normal line. And you will run across normals in physics and other places. It's always just a line drawn perpendicular to the surface. So put a little star. A normal is a guideline drawn perpendicular to a surface. Let's draw the sign for perpendicular. Perpendicular to a surface. And you can even use it as like an adjective. You could say the wave rays are normal to the surface, meaning they're coming in at 90 degrees. Okay. Now we're going to measure the angle of incidence, call that theta, with a little I, okay, so we'll define that down here. Theta I is equal to the angle of incidence okay, so incidence just means incoming waves of incidence, and that is always measured from the normal. Okay, so it's not measured from the surface. We don't measure up from the surface, we measure back from the normal. Okay, so if you're doing a lab or a question involved here, and you need to actually measure that angle physically, you would measure from the normal back. Okay, now it turns out that the reflection that's going to happen here, okay, because these waves are going to reflect off this barrier. I want an arrow. I'm going to reflect off this surface, okay, in such a way that that angle of reflection, theta r, the angle of reflection, is exactly equal to the angle of incidence. Okay, let's write a note of that. So what is the law of reflection? Well, the law of reflection is quite simply this. It is that the angle of reflection is always equal to the angle of incidence, and those are measured from the normal. Measured from normal. I think that's a pretty logical conclusion. All right. Okay, and so remember, these are just the wave rays. So there's actual wave fronts coming in here and coming out the other side. And it does get, sorry, the wavelength should be the same. It wouldn't change. Seeing as how we're dealing in the same media. You will get interesting interference effects here at this part because these wave fronts will interact. I'll try to find a real picture of this and put it in. Okay, so here's a picture we grabbed off the net, thanks to whoever originally took it. So we have a reflection barrier here. So I'll try to like just draw in on this picture, kind of what we're looking at here. Okay, so that is the barrier that the waves are bouncing off of. Let's put it like that. These are your incident waves here. What is it? It always seems to want to default to that. Okay, so here's your incident waves right here. And that's not an arrow. Struggling. We're going to get this. There we go. Okay, so there's your incident waves. And you can see the incident wave fronts are like here, here, oops. So your incident wave fronts are like here. I know there's a little bit of distortion, but you'll just have to kind of go with it. In here, and so on, right? So you can kind of see those are coming in. Now we draw our normal. We'll make it like yellow. So that's got to be at 90 degrees to the surface. So there's a normal. We could draw another normal here too if we wanted. Okay. And then we're going to draw the exit waves, or the reflected waves. Okay. So you can kind of see them down there. And you can see that there's an interference here. And your exit waves are these guys, right? Your reflected waves are these guys here. So right at these corners, you're going to get some waves crossing over one another. And you think you can see that in the picture, right? So you've got your incident waves traveling to the right, interfering with your reflected waves, and you get this kind of like checkerboard pattern. So that's what's going on there. Your incident angle is here. Your reflected angle is here, measured from the normal. And that's all we need to do with that.